Okay, good afternoon, everybody. So we continue today on our discussion on martingales. Today we will talk more on the submartingales, right? So recall that in your martingales, we have a filtration of sigma algebras. Okay, so this is a filtration, and then we have a random variable, integrable random variable, mn, which is measurable with respect to fn for each value of n. And then if you recall, right, our martingale means that this mm has to satisfy the this property over here, where the conditional expectation is equal to mn itself. Okay, so now if I relax the equality condition, okay, so that this becomes an inequality smaller or equals to, then we call this a submartingale. Okay, if I have the inequality the other way around, okay, then this is called a supermartingale. Okay, so you can see that if I have a supermartingale and then I take the negative, right, of these supermartingale, you will get back a submartingale. Okay, so it suffices for us to base our discussion all on submartingale. Okay, so whatever results we prove for submartingale, you can come up with a version for the supermartingale, right? You just take negative. Okay, so we'll just focus on submartingales. So for submartingales, we also have a similar martingale transform theorem. Okay, that says that if an, right, is predictable and bounded, but now we also require that the ans to be non-negative. Okay? Then your martingale transform, which is basically equals to this. Okay, so if I start with a submartingale, so mn itself is a submartingale. Okay, then it says that the martingale transform, right, with this predictable bounded and non-negative sequence, this will also be a submartingale. Okay, so this one the proof is exactly the same as before. Okay, so this is a submartingale, implies that this is also a submartingale. All right. Yeah, so the proof is exactly the same as before, and because of the inequality, that's why we need this to be non-negative. Okay, let's look at a simple example, right? Probably some of you have also encountered this kind of gambling strategy before. Let's say you are playing a casino game, right? And Sn is the amount of money that you win, your amount of winning, okay, how much you have won at time n. If you bet $1, okay, if you bet $1 every time step, right? So imagine this gambler, he basically plays the game by betting $1 for every single time step, and this Sn will be the amount of winning that he has at time n. Okay. So of course we start at x0 equals to 0. At the beginning, there's the initial winning is 0, right? So now you can think of a gambling strategy as a predictable sequence, as what we discussed last time. Okay, so if this is a predictable sequence, right? And moreover, let's assume your wealth, your whatever amount that you can bet, right, is finite, and of course is that means it's bounded, and of course is non-negative, right? Okay, so then you can form this your your martingale transform of the x of your xn. Okay, so before we do that, let's define to be xk minus 1. Okay, and let's suppose that this, so this is basically your increase in your winnings, right? How much winnings you have in the next time step, how much you win in the current time step, right? The increase in the amount that you have won. So that's keep things simple. Let's assume that it's either plus or minus 1, right? So you either lose $1 or you gain an additional $1. Okay, and let's assume that this is a Bernoulli distribution with probability p, right? So with probability p, you will gain $1. With probability 1 minus p, you will lose the minus 1. Okay. So one typical strategy to use is okay, at the beginning A1 equals to 1, that means you bet $1. Okay, and then after that, right, subsequently we are going to bet 2an minus 1. So I'm going to double the amount that I have betted the last time. Okay, if the outcome is negative. Okay, if I lose in the previous time step. Okay, and then you revert back to $1 if your outcome is positive, right? So you can see in this strategy, right, each time you are doubling your bet, and so as long as your mn minus 1, right, at this at n minus time n minus 1, your bet is successful, right? You will win back everything, right? All the amount that you have lost previously, you will be able to win back everything. Okay, right? So if this p is positive, right? If p is positive, that implies that this probability mn minus 1, or okay, mn minus 1 equals to 1 infinitely often, right? This will always happen, right? Infinitely often, this will be equals to 1. Okay, so so here I forgot to say we are assuming it's independent. Okay, these are all IID. Right, so definitely with probability 1, you will definitely hit, right? You will definitely hit the mn equals to 1, and then you will be able to win back everything, right? Okay, right. So yeah, okay, maybe yeah. So it means that it sounds like this is a sure win strategy. I think some of you will probably have already encountered this, right? So why don't we use this sure win strategy, right, in our gambling? Okay, which means that, right, if you every time you lose, you double your bet, and then eventually you will definitely win it back. Okay. But unfortunately, this, if you are in a casino playing this kind of game, right, your MN over here, this guy, right, whether you win or lose, this is typically a super martingale. Okay, so you do like this. That means the expected winning in the future, okay, is lower than the current MN. This is something that you should expect because the casino has to make a profit, right? They has to operate, so they usually has some built-in advantage to the casino, right? So in terms, if you look at it from an expectation point of view, on average, okay, your expected wealth in the future should be less than what you currently have. Okay, so your MN, if that's the case, if indeed is a super martingale, okay, which is usually the case for casino, then according to our martingale transform theorem, right? Let's say you use this predictable sequence as a strategy, then your winnings will be given by this martingale transform. Okay, so according to the martingale transform theorem, then this if this MN itself is a super martingale, then your martingale transform is also a super martingale. Which means what? Which means that my expectation of the martingale transform, which is your expected future winnings, right, is going to decrease, right? It's going to be less than, say, so right, is going to be less than what you currently have. Okay? Right, so in terms of the average value, you are actually going to lose. Okay, although it looks like with probability 1 is a sure win strategy, but with in terms of expectation, your amount of winnings that you have, right, according to this strategy, whatever strategy you use. Okay, so all your strategies are predictable, bounded, and non-negative. So no matter what strategy you use, okay, in particular, this is one possible strategy, right, which is a sure win with probability 1, but then your expectation is going to be decreasing. Okay, so it means that no strategy, right, even though this is a sure win strategy with probability 1, but in terms of expectation, you cannot beat the house. Okay, and in practice, you will find that this so-called sure win strategy will not really work in practice. So please don't go and try it, right? Because you can run into a sequence of very long minus ones. Okay? So there's a non-negligible probability that you will have a sequence of -1, quite a lot of -1, and because you are doing this doubling, the amount that you need to bet, right, will increase very fast exponentially. Okay, and you don't have infinite amount of capital, right? So you won't be able to sustain this strategy, and that's why, although it looks like a sure win, but in actual practice, nobody can sustain this strategy. Okay, so please do not try this. Okay, so that's just a interesting example in terms of gambling. But now let's look at what happens if I take a function of a martingale or submartingale. Okay, so we have a lemma that says that if I have a function f, okay, which is convex, okay, and of course I'm going to assume that f of my Sn, so Sn is either a martingale or submartingale. Okay, I assume these are all finite. Okay, so this function is quite well behaved. So so if my Sn, right, if my Sn is a martingale, or the Sn is a submartingale, but then if it's submartingale, then I also require that my f is increasing. Okay, so if either one of these conditions is true, then it implies that my Fsn is a submartingale. Okay, so this is submartingale. Okay, so proof is not difficult, so we just have to make use of Jensen's inequality over here, right? So for example, let's prove the first one. So if Sn is a martingale, I want to prove that this is a submartingale. So I basically want to look at this guy, Fsn, right? I want to show that this is smaller or equals to expectation of Fsm, okay, condition of Fn. So Fsn is equals to what? So Sn itself is a martingale, so Sn is equals to expectation of Sm, condition of Fn. Right, that is your definition of a martingale. And now because f is convex, so I can apply Jensen's. Okay. So this will be smaller than you interchange the bring the f inside the expectation. So Fsm, which is what we want, right? So this is true for all m bigger or equals to n. Okay. Right, so we have just proven that it is a submartingale. Okay, for the second condition is similar, right? So you can apply the similar argument here. Okay, the increasing is because down here, then we need to change it to smaller equals to, right? So that's why you need the f to be increasing. Okay, so a submartingale, naturally you should expect a submartingale, right? To be really just actually a martingale plus something, right? that because your expectation is for your submartingale, your expectation is increasing. So you should expect it to be actually consist of a martingale inside plus something that is increasing. So that is indeed the case. So Loop says that your submartingale can always be decomposed into a martingale plus an increasing predictable sequence. Okay, so Loop's decomposition says that, right, if I have Xn, and this is a submartingale, then Xn can be written as Yn plus Zn, right? Where my Yn, right, this is a martingale, and Zn, this is a predictable sequence. Predictable, and moreover, I start my Z0 equals to 0, and Zn is an increasing sequence. Okay, smaller equals to Zn plus 1 almost surely. Okay. And moreover, this decomposition is unique. Okay, so this is a unique, almost surely decomposition. Okay. Okay, let's give a quick proof of this. So the proof will proceed just by simply constructing the necessary Yn and Zn's to show that, right, indeed I can write in this way, and then proving that the whatever we construct, right, satisfy the property that this Yn is a martingale, this is a predictable sequence. Okay, so that's the part where we show that, right, it can be decomposed. Then the second step will then to show that this decomposition that we have constructed has to be unique, almost surely up to sets of measure 0. Okay, so since I need to satisfy this property, I will choose my Z0 equals to 0, right? So at the beginning, let's set Z0 equals to 0, and then I'm going to set my Zn to be sum of this xk minus 1 condition on fk minus 1, right? So I can always do that, right? The x are given, okay? We are given this submartingale, so I can put them together in this way to come out with my Zn, okay? And you can see that this is indeed, right, this is indeed a predictable sequence, okay? Because like the sum is up to n, so condition at most up to fn minus 1, right? Okay. Right, so it involves all the random variables here are measurable with respect to fn minus 1, so that's why Zn is a predictable sequence. So now we just need to okay, so after we have Zn, then the natural thing to do is to let Yn equals to Xn minus Zn. Okay, so this is just by construction. So then, of course, my Xn will be just Yn plus Zn. So now we need to show that. Okay, first let's show that we already know that it's predictable. So now we want to show that it's increasing. Okay, and moreover, the Yn is indeed a martingale. Okay, so that's to show that it's increasing. We just right. We just have to note that this term. Okay, so because Xn itself is a submartingale. Okay, so if I look at this term over here, minus xk minus 1, right? So this conditional expectation is bigger or equals to xk minus 1, right? Because your xk's this is a submartingale, so this bigger or equals to 0. So which means that all the terms inside here, right, are non-negative almost surely, right? So your Zn plus 1 will have an additional non-negative term almost surely. So your Zn, right, will be smaller equals to Zn plus 1 almost surely. So this implies that Zn smaller Zn plus 1 almost surely. Okay, so we have proven this one, and now we need to show that Yn is a martingale. So let's just have to verify it. So let's do a condition expectation of Yn given Fn minus 1, right? So by definition, this guy is expectation of Xn minus Zn given Fn minus 1. Okay. So expand it out. Okay. Minus, because Zn is a predictable sequence, right? Zn is a predictable sequence. So with the conditional expectation, it doesn't change it. So it's just still Zn. Okay, and then we notice that Zn minus 1, right? This is just expectation of Xn condition on Fn minus 1 minus Xn minus 1. Okay. So if I rearrange the terms, like take this guy, okay. So I want to replace this guy. Take this guy, so I can express this in terms of the Zn minus 1 plus Xn minus 1, right? And then I can plug in here, okay? And simplify, you will get Xn minus 1 minus Zn minus 1. Okay? And this, again, by definition, is just the Yn minus 1, right? Yn minus 1. Okay, so we have just proven that Yn is a martingale. Okay? So this is done, this is also done, right? Okay, so by construction, we're shown that indeed, right, your submartingale can be decomposed into a martingale plus an increasing predictable sequence. And then to show that this decomposition is unique almost surely, we will use induction. Okay, so use induction to prove that. So starting from Z0 equals to 0, right? So whatever decomposition that you use, it has to satisfy Z0 equals to 0. Okay, and then since it is a decomposition that looks like this, right? So if Z0 equals to 0, that means Y0 equals to S0. Okay, so this is unique, right? Your S0 is given, okay? Is the given sequence. So whatever decomposition you come up with, the Z0 and Y0 has to take on these two values, so it's unique for the index 0. Okay, so now let's suppose, right, by induction, let's suppose the decomposition is suppose uniqueness, right, up to n minus 1, okay, up to the n minus 1 term. So now if I do at any decomposition, Xn equals to Yn plus Zn, okay, that meets this criteria over here, okay, then I want to prove that this is also unique. This decomposition cannot take on any other ways. So Zn, right, so it has to be predictable, so that means Zn equals to Zn condition on Fn minus 1, right? Because Zn, no matter what decomposition you use, Zn has to be predictable. Okay, so now, yeah, so this guy Z, then because this is a decomposition, so your Zn equals to Xn minus Yn. Okay, and then you can expand this out. And inside, right, the Yn expectation of Yn given Fn minus 1, and this is supposed to be a martingale, right? So then this will be equals to Yn minus 1. Okay. So this guy, this is fixed, right? The Xn's are fixed, and the Yn minus 1 we assume, right, by your induction hypothesis is unique, right, up to n minus 1. So this is the Yn minus 1 is uniquely defined, okay? So which means that your Zn, okay, is unique almost surely, okay, right? Okay, so once Zn is, so this, okay, this implies that this is unique almost surely. So once Zn is unique almost surely because of this decomposition, right? Your Yn is just Xn minus Zn, so that means what Yn has also to be unique. Okay, so this is also unique almost surely. Okay, any questions here? Okay, so this is kind of a obvious result, I would say, right? So you submartingale, you should expect something like this. Okay. Okay, now we look at some more interesting results, which all, yeah, most of these results are derived by Du, right? So he's a very famous mathematician and probably basically an expert in probability theory. So he's the one who has been in the early days has been the pioneer for all these martingale theory. Okay. So we have all these results named after him, Luke's inequalities. Okay, so the first one is maximum inequality. Okay, so Luke's maximum inequality. Right. So if I give you Xn, Fn, this is a submartingale and is also non-negative. Okay. So for now, let's concentrate on the case where it's non-negative. That means all the Xn is bigger or equals to 0. Okay. Non-negative submartingale. Okay. And let's look at the maximum value that you have seen so far. So Xn star equals to the maximum of Xn of Xk. Okay. Sk, say, range from the starting index is 0 up to n. Right, so your Xk, this is a stochastic process, and we are looking at the maximum value that it has achieved in this stochastic process up to time n. Okay. So Xn star itself is also a stochastic process. So it's so similar to your Kolmogorov maximum inequality, right? We're also interested in the maximum value. So here we have a similar result as Kolmogorov. So given any threshold lambda non-negative, then this is true. So probability of Xn star bigger or equals to lambda, right, multiplied by lambda, or you can bring the lambda over, is fine, is smaller or equals to expectation of Xn on the set Xn star bigger than lambda. This is just an intermediate. So usually usually we will use this other inequality expectation of Xn itself. Right, so basically this tells me that the probability of Xn star, the maximum value, exceeding a threshold lambda is bounded by 1 over lambda of the expected value. And this is okay, later we'll show that indeed this is actually you will be able to derive the Kolmogorov's maximum inequality from here. So this inequality is actually more general than the Kolmogorov's one. And why we need all this inequality, right? Remember, it's very useful in your Kolmogorov's maximum inequality was used to prove the strong law of large number. Okay? So this inequality can be useful in a lot of other cases. Okay, so let's give a proof for this. So let's define a stopping time tau, which is the first time, right, that your xk is above the threshold lambda. Okay? So this is a stopping time. Okay, so see, because your Xn are all is adapted to this fluctuation, so this stopping time is a stopping time defined with respect to this fluctuation. Okay, okay, so this is a stopping time. So if I look at this Xn star, the maximum value, right, bigger than lambda, this set is equals to the set that the tau, right, is smaller or equals to n. Okay. So why is that? This guy means that, right, my xk, right, my xk for some value of k between 0 to n, okay, the xk value is going to be above the threshold, right? It's going to hit the threshold lambda, okay? Which means that, right, the stopping time, right, the first time that my xk hits the threshold has to be less or equals to n, okay? Similarly, the other way around, right, if my stopping time is smaller or equals to n, that means at some k, right, at some k smaller or equals to n is going to hit the threshold or exceed the threshold lambda. That means my maximum value, right, has to be bigger than lambda. Okay, so these two sets are equal to each other. All right, so now if I just take the indicator, okay, so this will be, so on this set, tau smaller equals to lambda, your maximum value, right, is going to be bigger or equals to lambda, right? So the x tau, the value at the hitting time, the stopping time, right, is going to be bigger or equals to lambda. Okay, and then you can, yeah, so according to the definition of this x tau, this is just nothing. You can write it as a sum. So xk tau equals to k. Okay. So now my xk, because my x, and this is a submartingale, okay? So my xk is smaller or equals to expectation of xn given condition of fk, right? For all k smaller or equals to n. Okay? Right, okay, so now if I take the indicator, I multiply the, okay, I just do xk with the indicator tau equals to k, right, and then take the expectation. So this guy will be what? This will be smaller or equals to expectation of xn. These are tau equals to k, right? This indicator tau equals to k is measurable, right, with respect to fk. So I can bring it inside of this expectation, and then the expectation outside, right, will remove the conditioning. Okay. So now if I look at this guy over here, right, this guy over here. Okay. I take the expectation on both sides for this. Okay. So I'm going to get lambda probability of tau smaller equals to n. Okay. So this will be what? Smaller or equals to, take the expectation of this. Expectation of this sum. Okay. And this inequality over here is true for all n smaller or equals to n, right? So I can apply the inequality inside the sum. So this will be smaller or equals to this side. So the xk can replace by xn. Okay, and then this expectation is nothing but the definition of x tau. Okay, don't need. So xn, right? So the sum over the indicator. So this is tau smaller equals to n. Okay, and then this guy is the same as this set over here, right? So we are trying to get this. So So this is expectation of Sn, and then S star bigger or equal to lambda. Okay. Right. So we have just proven the first inequality. Okay. And of course, the second inequality is obvious, right? Okay, because your Sn is non-negative. Okay. So this thing is smaller than Sn, right? So the second inequality is obvious. Okay. So from this inequality over here, immediately we get that the probability of Sn star bigger than lambda. Right, if I look at the x to power p, right, where p is bigger or equals to 1, where p is, so x power p, where p is greater than 1, this is a convex function, right? So we just saw before that, then, okay, Sn to power p, this is also a submartingale. Okay, for all values of p bigger or equals to 1, right? So now I can apply this same result, right? Apply the same result to Sn to power p, okay? Instead of just Sn, right? So as long as it's a non-negative submartingale, so this is certainly non-negative, it's a submartingale according to our previous lemma. Then I can apply this same result now instead to Sn power p. So immediately you get this is and of course the maximal value, right, is just raised to power p, right? Okay, so this guy, this probability will be smaller or equals to everything raised to power p. 1 over lambda p, expectation of Sn to power p. Okay? And this is true for all p bigger or equals to 1. Okay, so you find something interesting here, right? This result seems to be more general than this result, right? So in fact, like p equals to 1 is just a special case. You get back this result, right? But actually, this inequality comes from this one, right? So you have this thing, this kind of result are so-called self-improving. It improves on itself, self-improving inequalities. Okay, now let's look at a case where the how do we get the Kolmogorov maximum inequality from this Dup's maximum inequality? So recall that for Kolmogorov maximum inequality, we are dealing with the case where Xi, these are independent random variables. Okay. Without lots of generality, let's assume the expectation is equals to 0, right? So then we saw before Sn, right, where is the sum, the partial sum of the Xi up to n. We saw before that this is a martingale. Okay. So this is a martingale. So now we can apply the Dup's inequality on this martingale. Okay. So a martingale is just a special case of a submartingale. So I can apply Dup's inequality on a martingale. Right, so Dup's inequality says that, right, the probability of these Sk bigger or equals to lambda. Yeah, so here to apply the Dup's inequality, I need the submartingale to be non-negative. So I was not quite right just now when I say apply to this martingale. In fact, I need to apply it on the submartingale, which is taking the absolute value, right? So because my Dup's inequality, okay, my Dup's inequality only applies for non-negative submartingale. Okay. So this is a martingale, but then taking the absolute value, right? This is a convex function. You will change it to a submartingale and it's non-negative. Okay. So now I apply Dup's inequality here. So this absolute value of Sk, this is a non-negative submartingale. So this will be smaller or equal to 1 over lambda square of Sn square, right? So if I take p equals to 2, so this, then the absolute value can go away, right? Okay. So, but you see, this guy is nothing because is the x size are independent. This guy is just a sum of the variances, okay, which is what we have in the Kolmogorov maximum inequality. Okay, so this result is just basically the Kolmogorov maximum inequality. All right, so you can see Luke's maximum inequality is stronger, right? It's more general than this Kolmogorov. Okay, any questions here? Okay, if not, we go on to prove another of Luke's inequality. So now we need some background first. Okay, so recall that if my random variable is in LP, okay, in the space LP means the norm, right? The norm is defined to be expectation of x raised power p, and then take 1 over p, okay, root 1 over p, and then this guy is positive, is non-finite, right? It's finite. Sorry, this guy is finite, okay? So then we say that x, right, is in this LP space. Okay, and then you have this famous Holder's inequality, which says that, right, if my p is finite and is bigger or equals to 1, then I can define a Q, right, which satisfies this 1 over p plus 1 over q equals to 1. Okay. Then Holder's inequality says that, right, xy under the 1 norm, this is smaller or equals to xp and multiplied by yq. So this is your Holder's inequality. So I'm not going to prove this guy here, but this is like kind of a standard result you can find in a lot of textbooks. Okay, so now we have a lemma that says that, right, again, x, y, these are non-negative random variables, and expectation of y power p is finite, okay, where your p is strictly bigger than 1. And moreover, you have this property that for all lambda bigger or equals to 0, x, the tail probability of x, okay, probability of x bigger or equals to lambda multiplied by lambda, this is bounded by expectation of y on the set x bigger or equals to lambda. So you are given this, right? This is a condition. You are given these two conditions, then this implies that my xp, okay, my x with the norm p of x, okay, is smaller or equals to p divided by p minus 1 of the norm p of y. Okay. So we will need this result later in the inequality, the Luke's LP inequality that we are going to prove. But let's quickly prove this lemma way. Although it may look a bit cryptic, right? These are conditions that are given, especially this one looks a bit cryptic. But let's say, right, you are given these properties, then you can then conclude this guy. Okay, so let's give a quick proof. This is more of a calculus thing, okay? So let's see. So let's let Sn to be the minimum of x and n. Okay. So we are going to define this sequence of random variables, and this will be well behaved, right? Because I'm taking x and the minimum of n. Okay. Right. So now I can write expectation of x n power p to be okay, so we need a simple result that says that, right, if I have z to our p, this is nothing but if I take the simple Riemann integral, it's just integrate from 0 to z x p minus 1 dx, right? So you can easily verify that this is true. Okay. And moreover, this guy can be written as integration from 0 to infinity as p minus 1, and basically restricting my x to be smaller or equals to z. Z bigger or equals to x. Okay. So if I apply this simple result over here, right, to the z replaced with the xn, okay, I will get this is equals to expectation of what, p integral 0 to infinity as p minus 1, right, xn bigger or equals to x dx. Okay, so now I can apply Fubini here to interchange this expectation with is nothing but an integral with this integral. Right, you can apply Fubini here is because, right, the integrand, right, is non-negative. So we have yeah, right, because this integral is from 0 to infinity. This is non-negative, so I can apply Fubini. So 0 to the p take outside, 0 to infinity, and then the expectation, this integral goes inside, it will change this indicator, right, to become a probability. It's p minus 1 probability of xn bigger or equals to x. Okay, now I will apply this condition that's given over here, right? This probability, wait, this guy. Yeah, so this xn, right? Xn is smaller or equals to x minimum with n. So this probability will be smaller or equals to probability of x bigger or equals to x, and then I can then apply this condition over here, right? So this will be smaller or equals to p. So apply this condition here is y indicator of x bigger or equals to x. Okay. So now I can apply Fubini again. I can interchange this integral with this expectation, right? These are again two integrals. So apply Fubini again to interchange. So this take the expectation outside, and then the integral will go in, take the expectation outside, right? So you have expectation integral of this whole thing. But this integral is with respect to the x dx, right? So it doesn't affect the y. So I can pull the y outside of the integral. That's p minus 1. Yeah, there I made a mistake. Oh, there's a lambda. Wait. Yeah, there's a lambda over here. So I need to, the x is the lambda, right? So divide by x. So this p minus 2. Sorry, p minus 2. Okay, so xp power p minus 2, right? With the rest remains the same. Okay. And then this guy, right? This guy, if you look at this result over here, is nothing but x power of now is p. This is p minus 2, so this becomes p minus 1, right? So this p expectation of y x p minus 1. Okay. Okay, and now sorry, because there's a p here, right? The p becomes p minus 1. So this integral, right, is this guy over here divide over the p minus 1, right? So it becomes p over p minus 1. Okay. So now I can apply the Holder's inequality over here, right? So these are two random variables multiplied together with and this is the one norm, right, of the product of these two random variables. So apply Holder's inequality. This is smaller or equals to P over P minus 1, Y with the P norm, and then X P to power P minus 1 with the Q norm. You can verify that, right? This can be simplified to X with the P norm but raised to power P minus 1. Okay? So we can easily verify this. Okay. Okay, and now I can let my n go to infinity and apply Fatoul's lemma. So my X with the P norm, okay, this will be according to Fatoul's lemma, right? This will be just smaller or equals to lim in of the expectation of Xn to power P, right? Okay, Xn go to infinity. And now this expectation is smaller or equals to this guy. Okay, so it's smaller or equals to P over P minus 1 Y of P norm X P minus 1, right? And then finally, by simplifying this, right, you cancel out the P minus 1 power, right, on both sides. You will get the X P norm without the power is smaller or equals to P over P minus 1 multiplied by the Y P norm, right, which is what we are trying to prove over here. Okay, so this is more of a calculus result. So now let's use this to prove the Dup's LP inequality. Okay, Dup's LP inequality. Right, so it says that if Sn, this is a non-negative submartingale. Okay, and let's choose for P strictly bigger than 1. Okay. Then we have Sn star, right? Sn star is just the maximum of the Sn, okay, up to time n. Okay. So Sn star with the P norm is smaller or equals to P over P minus 1 of Sn with the P norm. Right, just now we proved the maximum inequality, which is just saying that the probability, the tail probability is smaller or equals to, right, 1 over lambda of the expectation. But now we have a result that involves the expectation of the P's power of the maximum value, okay? Then it's modeled like this. In fact, this guy, the proof is actually kind of obvious. We have already done all the work. So all we need to do is to apply this lemma over here. Okay, so what we can do is to replace the x here with the Sn star, okay, and replace the y with the Sn, right? So x becomes Sn star, y becomes Sn. Right, so all these conditions hold true, right? This is what we saw just now, right? The maximum inequality. So lambda probability of Sn star bigger or equals to lambda is smaller than this expectation of Sn, right? Y becomes Sn. Expectation on this set where this is the Sn star bigger or equals to lambda, right? Okay, this guy over here, right? Okay. So the maximum inequality plus this lemma, right, immediately gives us this. Okay. So really no need to prove, right? So all the work has been done. So any questions here? Okay, so this LP inequality only applies for the non-negative submartingales. So for a general Sn, right? You can always come up with similar results, but then you have to look at Sn, the positive part, right? So if Sn is a general submartingale, then Sn, the positive part, this will be a non-negative submartingale. Okay, right? Taking the positive part, this is again a convex function. So this is increasing, right? So this is a non-negative submartingale. Okay? So in general, this is a non-negative submartingale. So then I can apply these loops LP inequality on this Sn plus. Okay. Right. So in particular, okay. So in particular, you will get Sn star p. So this will be smaller than the one where we look at the positive part, right? Because Sn is the Sn plus minus Sn minus, right? The positive minus the negative part. So this guy will be smaller than this, and then I can apply the LP inequality on here, so that now we can get p over p minus 1, but now this is Sn plus. Okay, so you will be able to get a result that looks like this. Okay. Okay, any questions here? Okay, if not, we now come to another very important concept, which is the notion of uniform integrability. So let me see. I think so. The discussion next will be more general, not just restricted to martingales or submartingales. Okay, but then next week we will make use of this concept of uniform integrability to prove convergence of these submartingales. Okay, so this definition will apply to any stochastic process. So we say that, right, I have a stochastic process. Okay? We say that this is uniformly integrable. Okay? If the expectation of Sn on the set where Sn is bigger than some constant k, okay? And then I'm going to take the supremum over all possible values of n. Okay? Right? So for all the elements inside this stochastic process, the tail expectation, okay, for some k, this has to go to 0, right, as k goes to infinity. Okay? So if I look at the extreme tail of every random variable inside this stochastic process, then its expectation, right, will go to 0. Then we say that this is uniformly integrable. Okay? So certainly, if I give you a uniformly integrable stochastic process Sn, then okay, so if Sn is uniformly integrable, then that means what? I can find k sufficiently large. Okay, by definition, right? I can find k sufficiently large such that this guy is very small, right? Supremum of so let's say this is smaller than 1, right? So for k sufficiently large, okay, this will be smaller than 1, right? Because it is converging to 0. Okay, so what does this mean? This means that the supremum of the Sn itself, okay, because expectation of Sn, right, is equal to expectation of Sn on the set where is smaller than k plus expectation of Sn indicator bigger than k, right? But this guy is less than 1, okay? and then on the set that is less than k, right, the expectation is less than k. So this is smaller than k plus 1, right, which is finite. So it means that, right, if it's uniformly integrable, then my expectation, right, is also uniformly bounded. Okay? It's uniformly bounded, but the converse is not true. So the uniform integrable is stronger than just saying that the sequence, right, the expectation is uniformly bounded. You can easily come out with counter examples, okay, to show that even if you have a uniformly bounded sequence, right, uniformly, your expectation is uniformly bounded, you may not be uniformly integrable. Okay, so you can come up with some simple examples and you can see that this is true, right? So the converse doesn't hold, but yeah, but uniform integrable will imply is uniformly bounded. Okay, so let's look at some examples here. So if my sequence Xn is bounded almost surely by some other random variable, okay, and moreover this expectation of y is finite. Okay, so then what happens? Right, let's look at this guy, bigger than k, right? So this Xn is bounded by y, right? So this will be smaller or equals to y, and then the Xn here can also be replaced by y, right? Because Xn is smaller than y, so this set here is smaller than the set where y is bigger than k. Okay, so yeah, but the expectation of y is finite, okay, which means that as k goes to infinity, okay, this tail expectation, right, has to go to 0, right, because otherwise the expectation will be infinite. Okay? So this guy is going to 0 as k goes to infinity. Okay, so it means that, right, if my sequence is uniformly bounded, okay, by some integrable random variable, then is uniformly integrable. Okay, so this is just one example. But of course, it's not always the case. This is just a sufficient condition. Okay. So you can also find a lot of other conditions from, if you look at Dirac's the textbook, right? There are also a few other sufficient conditions you can check to see whether the sequence is uniformly integrable or not. Okay, so now let's come to a result. So we want to prove that, okay, if X is in L1, okay, right, so with this sigma algebra, okay, so your underlying sigma algebra is F, then the collection of sets, the collection of random variables as condition on F prime, okay, where F prime is just a sub-sigma algebra. Okay, so this is a sigma algebra, right, inside F. Okay, so this whole collection is uniformly integrable. Okay, so maybe I need to point out, right, although I talk about a stochastic process, it doesn't mean that this has to be a sequence. Okay, so it can be any collection, okay, any collection of random variables. As long as it satisfies this, then we say that it's uniformly integrable. So we can see that this is a very big collection of random variables, right? These conditional probabilities, conditional expectations are all random variables. Okay, so this set of random variables is uniformly integrable. So we want to prove this result. Okay, so to prove this result, I need something else first. So let's prove a simple lemma first. So it says that if X is integrable, okay, then for all epsilon bigger than 0, I can always find a delta, okay, such that, okay, whenever, okay, whenever A, right, so for all A with probability of A being smaller than delta, okay, so I take any set A that has probability smaller or equals to delta, then it's true that if I take the expectation of x on A, this is smaller than epsilon. So given any epsilon value, no matter how small, right, I can always choose a small enough delta so that this expectation, okay, for any over any set A, right, where he has very small probability, right, smaller than delta, then this expectation is smaller or equals to epsilon. Okay, so that's how I prove this. Right, if probability of A is smaller or equals to delta, then for any, okay, then we have this expectation of x on A, right? I can again break it down into two parts where these are absolute value of x is bigger than k or smaller than k, right? So if it's smaller than k, then this expectation will be bounded by k probability of A, right? And then plus the other part where it's bigger than k. So expectation of x, where now x is bigger than k, and I can in fact throw away the indicator on A, right? Because this indicator will be bigger than the one with this guy and A, right? So I can ignore the A part, okay? So now if you look at this guy over here, the probability of A is smaller than delta, right? So I can, so replace this with just K delta plus this guy over here. Okay, so now I can choose my K to be large enough, okay? Because my X is integrable, right? So I can choose my K to be large enough so that this part is small, right? So in particular, I can choose my K to be large enough so that this part is, say, is smaller than epsilon over 2, okay? And then I can set my delta, right? So then I can choose my delta to be epsilon over 2k. Okay, so choose delta equals to epsilon over 2k, and then choose, okay, first of all, I choose k to be large enough, right? Sorry, thanks. So choose k large so that this part A, right? This A is smaller than epsilon over 2, okay? Which I can always do because x is integrable. So I choose k large so that it's smaller than epsilon over 2, and then after I fix the k, I can choose my delta, right, to be equals to epsilon over 2k. Okay? So then these two combined will be less than epsilon, okay? Which is what we are looking for, right? So that means I can, and moreover this k, right, it only depends on x side, it doesn't depend on A. Okay? So it means that, right, as long as I choose my delta to be epsilon over 2k, right, small enough, then for all sets A, right, this is always true. Okay, okay, any questions here? Okay, so this is the lemma, and now we want to prove this result. Okay, I want to prove that this guy over here is uniformly integrable. Okay, so I let this, let this equals to y for simplicity. So basically, right, y equals to this for some f prime, okay, for some fixed s prime, let's call it y, is the conditional expectation of x given f prime. Okay? So I want to solve, okay, right? So let me write here. So let y equals to x condition f prime. So what do I want to show? I want to show that, right, this guy expectation of y, and then according to the definition of uniform integrability, right, I want to show that this is going to 0, right, as k goes to infinity. Okay. All right. Okay. So what should we do? So that's fix epsilon. So fix epsilon bigger than 0, and then we are going to choose a delta, right? as in the lemma that we have just proven, right? So for this given x, okay, for this given x over here, for any fixed epsilon, I can choose a delta so that this is true, right? For all small sets A with probability less than delta. So I choose the delta according to that lemma. And now I can also pick a k, right? Pick a k large such that 1 over k of this guy, okay? Because x is integrable, is finite, so that means I can always find k that is large enough so that this guy is smaller than delta, okay? The delta that we have chosen. All right, okay, so if I let y to be this, then the Jensen's inequality tells me that this guy is smaller than expectation of x, right? With the absolute value inside the expectation, so Jensen. Okay, now we can try to now bound this guy. Okay. So expectation of y okay, so this is what? This is smaller or equals to right, the y, right, we just show that y, absolute value of y is smaller or equals to this, so let's plug that in. Okay, and then basically replace the absolute value of y by this, because this guy is smaller than this, so I can just replace it with this. Okay, and this guy here, this set over here, right, this is measurable with respect to f prime, so I can bring this indicator inside the expectation over here, and then so this guy will be just expectation without the conditioning. Right. Okay, now let's look at this set over here, right? Maybe let's call it A, right? This set over here. So what is this? The probability of A. Okay. So according to Markov inequality, right? This random variable bigger than K. So probability of A from Markov inequality is smaller or equals to 1 over K of the expectation of this random variable, right? But expectation of this random variable is nothing but expectation of x, right? Okay, and then we have chosen the k big enough so that this is less than delta. Okay, so the probability of A is less than delta, and because the delta was chosen, right, according to that lemma over there, just now that we proved, so then that lemma tells me that, right, this expectation, okay, is smaller than epsilon. All right, so we are done, right? So we have just shown that for sufficiently large value of k, I can make these to be as small as desired, right? For any epsilon bigger than 0. Okay. Okay, so it means that this all the y's, right? All the y's over all the possible f pi's, this is uniformly integrable. Okay. Okay, there's another result that may be useful. So if I give you a function phi that maps to non-negative values, okay, and moreover x over phi of x, this guy is converging to 0, right? As x goes to infinity. Okay. Yeah, so for examples of such phi's, for example, phi x equals to x power p, right? Where p is bigger than 1, or x log x, right? Okay. So things like this, right? So the phi x is growing faster than the linear function. Okay. So now if I can verify that expectation of this phi of xn, okay, so apply the phi to the xn, I can verify that this is uniformly bounded, okay, smaller than some constant c, right, which is finite, okay, uniformly bounded for all n, okay, inside my collection of random variables. So if this is true, then it implies that the xn, okay, is uniformly integrable. Okay. Right. So if I can find a function so that, right, this expectation is uniformly bounded, then it implies uniform integrability of the original collection of the random variables. Okay, so let's prove that. So this is actually also a good way to check whether your set of random variables is uniformly integrable or not. So why is that? So that epsilon k to be supremum of x over phi x, where x is bigger or equals to k. Right. So according to this condition over here, as k goes to infinity, right, this epsilon k is going to 0. Okay. So this is going to 0 as k goes to infinity. Okay. So now we have expectation of xn, right? We want to show that this guy is going to 0. So according to the definition of your uniform integrability, so this guy is going to be bounded by what? If I replace the xn, right, with the phi of xn, okay? So this will be bounded by the epsilon k multiplied by, now replace with the phi of the xn. And then this remains the same. Okay, so and then and then we saw that this guy, right, this is if you already verify that this is uniformly bounded, then of course this one over here will be smaller than this, will be smaller than c, right? So this will be smaller than the constant c, right, epsilon k times c, right? And then of course as k goes to infinity, because the epsilon k is going to 0, right? So this thing is going to 0. Okay, so it's a very simple proof, but it's quite a powerful result in the sense that it makes things very easier for you to check, right? As long as you can come up with a function that is growing faster than the linear function, and then moreover, if you apply it to your set of random variables, right, and you can prove that it's uniformly bounded, then you can conclude that your set of random variables is uniformly integrable. Okay, any questions? Okay, so now we come to the important result. Okay. Okay, so Xn, right? Xn is a set of random variables. So the index is inside some set, some general set n. Okay. And you're also given another x. Okay. And then all of these are integrable. Okay. So all of these are integrable. These are all integrable random variables. Okay, then the following statements are equivalent. So the following statements are all equivalent. So the first statement says that Xn converges to X in L1. Okay. Which means what? The expectation of Xn minus X, right, is converging to 0 as n goes to infinity. Right. So convergence in L1, Xn converges to X in L1 is equivalent to saying that Xn is uniformly integrable and converge in probability. Okay, so they are equivalent, which means that, right, if I give you a uniformly integral sequence and moreover is converge in probability, then you can conclude that it's converging L1. And it's also equivalent to saying that Xn, right, expectation of Xn is converging to expectation of X, and also the sequence itself is converging in probability. Okay. So all these three statements are equivalent to each other. Okay, let's prove this statement here. So what we are going to prove is 2 is implying 3, implying 1. Okay, so we prove 2 implies 1, and then 1 implies 3, and then 3 implies 2. Right. So if we can do that, then we have proven that all three statements are equivalent. Okay, let's prove the first one. All right. So 2 implies 1. Okay. So yeah, given that it's uniformly integrable and it converges in probability, okay, I want to show that it's converging in L1. Right. So for any epsilon bigger than 0 and any k bigger than 0, so we want to find a bound from this guy, right? Okay, when n is sufficiently large. So this I can bound it by on the set where is smaller than epsilon, and then plus the part where is bigger than epsilon. Okay. Right, and then I can break this down. So this will be smaller than the absolute value of Xn plus absolute value of X, right? So I can break this into two terms. Okay, and now I'm going to consider the case where your Xn is smaller than k, right? For any constant k, smaller than k or bigger than k. Okay, so I can bound it further, whereby if it's smaller than k, right? If it's smaller than k, then this guy will be smaller than k, and then the expectation will just becomes the probability. Okay, and of course, this is an upper bound. I can ignore the part where it says smaller than k, right? So plus k probability of Xn minus X bigger than epsilon, right? And then plus the part where is bigger than k, right? So of course, I can now actually ignore this one, right? Because I'm just finding an upper bound. Okay. So this guy is bounded by this. So we can do a similar thing over here, right? You can apply the same technique to also get two terms. Okay. So in fact, the first term will be the same. So this becomes 2, and then plus. Okay, so now 2 means what? Is uniformly integrable and is converging in probability. So converging in probability means what? This guy, right, is going to 0, right? Converging to 0 as n goes to infinity. Okay, so this part is done. So this will go to 0. Okay, and then how about this part? is uniformly, okay, so of course this is smaller than the soup, right? And because it's uniformly integrable, this soup, right, is going to 0 as the k goes to infinity, right, as k is very large. And of course this one, right, because x is integrable, so as k goes to infinity, this part is also going to 0. Okay, so which means that if I take, right, if I let my okay, if I take my n to be very large, okay, this will become very small. In fact, I can choose n sufficiently large so that this whole thing, right, is less than this guy is less than, say, epsilon, right? Or okay, I can choose my n sufficiently large so that this whole thing with the 2k, right, this whole thing is less than epsilon. And then after that, I can set my k, right, to go to infinity so that this part goes to 0 and this part goes to 0. Okay. Okay, so then that means, right, this whole thing is going to 0, right? So taking the lim suit of this guy as n goes to infinity, we have just shown that this is equals to 0. Okay, the lim suit equals to 0. Okay, so we have just shown that the 2 implies 1, right? So the convergence in L1. Okay, any questions here? Okay, now we want to show what 1 implies 3. So this one should be easier. So 1 implies 3. Right, so yeah, so we just have to apply Markov. So we know that this is going to 0. So to prove that the convergence in probability, right, is just a matter, is just using Markov, right? So 1 over epsilon of the expectation of xn minus x. Okay, and so this guy is 1 means that this is going to 0, right? So this goes to 0. So this probability goes to 0. That means it's converging in probability. And then how about this one? So this one is just applying this inequality over here. Right. So this is smaller than the right. Okay, so smaller than the expectation of xn minus x, which go to 0. Okay, so 1 implies 3 is obvious. Okay, so now we need to prove 3 implies 2, right? From here to here. So I need to prove that it's uniformly integrable, right? The converging probability is already assumed. Okay, so I need to use these 2 to prove that it's uniformly integrable. Okay, so I want to prove 3 implies 2. Okay, so the main part is to prove the uniform integrability. Okay, so first of all, right, we are given that this expectation converging to this expectation. That means for n sufficiently large, this guy will be very close to this guy. Okay, so let's say n bigger than some n naught, we have expectation as n is less than this plus, say, epsilon over 2, right? Okay, for a fixed epsilon bigger than 0. Now I can define a continuous function called, say, phi k of x. Let it to be equals to x when x is inside 0 to k minus 1. Okay? and it's equal to 0 when x is bigger than k, and is a linear, right? A linear part when x is between k minus 1 and k. Okay, so basically it looks like this, right? From 0 to k minus 1 is equal to x, right? Okay, equals to x. And then from k onwards is equal to 0, right? So in order to make it into a continuous function like that, basically just take a linear, right? Okay, a linear function over here. Okay, so this phi k is a continuous function. And moreover, right, as k goes to infinity, for any fixed value of x, this phi k of x, right, is converging to x, okay, as k goes to infinity. Okay. And you can see that this phi k of x, right, is bounded by x. Okay, so now so since it's bounded by x, right, this phi k of x is bounded by x. I can apply and moreover is converging to x, right, as k goes to infinity. So I can apply the DCT, right, the dominated convergence theorem. So DCT tells me that if my k is very large, okay, then the expectation of this phi k of x, okay, is going to converge to the expectation of x. Or rather, here I'm going to apply the absolute value. Okay, so expectation of absolute value of x will be close to the expectation of the phi k of the absolute value of x, right? Okay. So when k is very large, this will become very small. So this one will be smaller than, let's say, some smaller than epsilon. Right? I can choose my k to be large so that this is smaller than the epsilon value. Okay, and now I can also do at this case where now my k is fixed, but my n, I'm looking at n going to infinity. Okay, and we saw that we are given that this xn, right, is converging to x in probability. Okay, and this guy, okay, this guy is bounded, right? So as n goes, so I can apply the DCT again. So now this DCT is applied for the n going to infinity instead of the k going to infinity. So I can apply the DCT again over here. Okay. Okay, maybe I didn't really go through this. So for xn going converging in probability, right? The DCT will also hold. Remember, we proved the DCT for xn converging almost surely, right? So and then you actually have a result. We did show a result that says that if xn converts to x in probability, then for any subsequence, right, of these xn's, I can always find a subsequence whereby the xn is converging to x almost surely, right? Okay, so then you can use that result to prove that the DCT will also hold. Okay, will also hold when my xn is converging to x in probability. So here I apply the DCT here. Okay, so I bring the limit from outside the expectation to inside the expectation, and then okay, and then because my phi k, right, is continuous, so then I can bring the limit inside the phi k, right? So this guy is converging to n goes to infinity to phi k of x. Okay. Okay, so now we have all the ingredients. Okay, so my xn. So I want to prove that it's uniformly integrable, right? So I want to prove that this guy is small. So this is smaller than expectation of xn minus expectation of phi k of xn. Okay, right? Because you can see from the definition, right? Your x is the linear function. X is bigger or equals to this phi k of x plus x on x bigger than k. Right? Okay. Right, because it's just this part. This part is different from the linear function x. Okay, so you break it into two parts, right? This is definitely true. Okay, so this is true, right? So now I can yeah. So now this bound, okay, this will be bounded by expectation of. Okay, so we can make use of this first bound over here. So bounded by expectation of x plus epsilon over 2, and then we have this other bound where this guy is very close to this guy, so it will be also be within this guy plus epsilon over 2 or minus epsilon over 2. So this will be overall will be bounded by this, then epsilon, right, plus at most epsilon, okay, plus epsilon. And then this part, right, because I've chosen my k to be large, so this is smaller than epsilon, so this being also smaller than epsilon, so overall smaller than 2 epsilon. Okay, and this is true for any epsilon that I can choose, right? I can choose any arbitrary small epsilon, and then I can choose my k to be sufficiently large so that this is true, okay, and n sufficiently large so that this is true. Okay, so I just show that this is uniformly integrable. So any questions here? Okay, let me see. I run out of paper. Okay. Okay, I'm going to just go through one more definition, and then because this definition you may need some time to get used to, so I want to go through it, and then most of the results that we're going to prove we will defer it to next week, okay? So that you at least have some time to sleep over it and get used to this definition. Okay, so this is called okay, so first of all, right, my martingale or submartingale, right, the index set, I can actually generalize it to any general index set n that is so-called totally bounded, totally ordered set. Okay? As long as I have a totally ordered set, okay, so what does it mean? It means that, right, so this is any index set. Totally ordered means that for all values of n and m, okay, inside this set over here, I can say that either n is smaller or equals to m, right? So this so-called smaller or equals to is a relationship that you can define. Need not be the usual smaller equals to in the numeric sense, right? So this is just a relationship. Okay, either n is related to m in this way, or m is smaller or equals to n in this way. Okay, and of course this relationship has to satisfy the transitive property, and if and n is smaller or equals to itself, right? And so on. Okay, the usual properties, right? So n is smaller or equals to n, and moreover, if n smaller or equals to m, m smaller or equals to n, then that means that, right, n equals to m. Okay. And okay, let me just write now if n is smaller or equals to m and m smaller or equals to k, that implies that n smaller or equals to k, right? Okay, so this is a very general version, right, of the normal, index set, right, that you think of it as the time indices. But we can actually use a very general so-called totally ordered set, okay, for our index set. And then we can define our filtration. So Fn, right, is a filtration. Okay, where now my n belongs to this totally ordered set. And we say that it's a filtration if Fn is inside Fm, okay, if for all n smaller or equals to m, okay. So according to this relationship, okay, as long as n is smaller or equals to m, then this similar algebra is inside this similar algebra. Then we say that this is a filtration. Okay. Yeah, so why do we want to do this kind of generalization? So you'll see later, I will give an example. But let's now introduce this concept of a submartingale. Okay, so once you have a filtration, you can define your submartingale according to just now the definition that we use, right? Except that you keep in mind that this smaller equals to refers to this total order, okay, inside this in that set. So I have a submartingale Sn Fn. Okay, so we say that this submartingale is right crucible. Okay, it's a right crucible submartingale if my Sn is smaller or equals to expectation of x condition on Fn for all indices n, okay, and for this x, this is for some very special random variable x, okay. So this x need not appear inside here, right? So if I can find a random variable x, okay, such that this property always hold, the Xn is smaller or equals to the conditional expectation of this x. Okay, and moreover, this is a integrable x. Okay, now this smaller equals, there's an abuse of notation. The smaller equals to here refers to the normal, your normal numeric, right? Your numeric smaller equals to. Okay, the smaller equals to here refers to the one inside your index set. Okay, so this is a normal numeric smaller equals to. So we say that it's right crucible, right? If I can find an integral random variable, okay, so that it serves as an upper bound. Okay, if it's for martingale, then right, if martingale, then of course we replace this smaller equals to with the equality. Okay, then we say that the martingale is right crucible. Okay, so in particular, if there exists some n naught inside this totally ordered set, okay, in such a way that right, this n naught is the maximal value inside this totally ordered set, right? So that means by n smaller or equals to n naught for all n inside this index set n. Okay, so n naught is like your maximal value. Right, then according to, if this Xn is a submartingale, right, according to the definition of this submartingale, then Xn, right, by definition is smaller or equals to expectation of Sn naught, right, condition on Fn. This is just the definition of your submartingale. Okay, so if this is the case, then right, so then my X will be nothing but the Sn naught, right? Okay, so then this particular submartingale is right crucible, or in this case, since the X itself is part of the submartingale, then we say that this is right close. Okay, right close. So instead of right crucible means you can find, right? You can find this additional random variable to make this bound to be a universal bound. But now, if this random variable happens to be also, an element inside the submartingale, then we say that it's right close. Of course, if I have a right closable submartingale, right, I can find a X. Okay, so that this is true, I can always add it to my submartingale to make it right close, right? So I can always define the some n naught, right? So I can define a n prime to be n union of just some special n naught, right? So I choose a special n naught. Okay, I take the union, and then I define my total order in such a way that, right, everything here is smaller or equals to n naught. Okay, and then I will just then set x n naught to be equals to x, right? If it's right closable. Okay. That means I can include it inside the submartingale. Then of course, then it becomes right close. Okay, so right closable, just you can always make something that's right closable into right close. All right. Okay, so let's do one example why this is useful. Okay, now I have a sequence of IID random variables. Okay, SK. These are IID. Okay. We saw before this Sn, right? Sk. Okay. This Sn is we saw before this is a martingale. Okay, but today we are going to create something else. Okay, so let's let the index set n to be the set of negative integers. I'm going to take the set of negative integers, and of course the relationship, right? The smaller or equals to relationship will be just the ordering of the negative integers. Okay, so let's consider this as my index set. And now I'm going to define my filtration, okay, f minus n, right, where n is so for any n bigger or equals to 1, right? So this minus n is inside the index set. So this f minus n is, I define it to be the sigma algebra that's generated by Sn plus 1, and so on, right? Which is the same as saying the sigma algebra generated by Sn plus 1, right? Because Sn plus 1 is just Sn plus 1, right? Okay, so it's the same as the one generated by Sn, but now just Sn plus 1, Sn plus 2, and so on. So you can see, right, this guy over here, this is a filtration because f of minus n plus 1 is inside f of minus n, right? So minus n plus 1 is smaller or equals to minus n, right? So according to the ordering of the negative integers, okay, right? So this guy is smaller than this guy, and this sigma algebra is inside this sigma algebra, right? Because the minus n plus 1 is the one without the Sn, right? Okay, so this one is inside here. So it means that, right, what I've created here, this f minus n, okay, right, this guy, right, this is a filtration. So now we can observe that my expectation of x1 condition of f minus n. Okay, by symmetry, right? Because they are IID, and also the x1, x2, all the way to xn. These are all inside the Sn. Okay, so by symmetry, right? This conditional expectation is the same, right? So for all k, right, up to n, okay, because your Sn, right, is the sum, right? The sum is doesn't depend on the ordering, right? So all the x1, x2, x3, everything all up to Sn all appears in Sn. Okay, so condition on the Fn minus 1, which is generated by this guy, all of these are the same, right? All these conditional probabilities are the same. Conditional expectations are the same, right? In fact, you can prove it rigorously from from the basic definition of conditional expectation, you can prove that these are the same. Okay. So now I can look at Sn, which is just right because Sn is inside here. So condition on f minus n, right, is just itself, right, is measurable with respect to f minus n. Okay. And now I can break down the Sn into the sum of the xk's, right? So k from 1 to n. And because they are all the same, right? They are all equal to the conditional expectation of x1. So this will be nothing but n times conditional expectation of x1. Okay, so you can see that, right, if I define z minus n to be Sn divided by n, so take the n over Sn divided by n, this is nothing but expectation of x1 condition on f minus n. Right? And since this is, so I think we proved this in the discussion on the martingale, right? So if you have a filtration, you have a random variable, right? This is fixed, the x1 is fixed, it's not changing, but it's the conditioning on a filtration, right? Then this guy is a martingale. Okay, so z of minus n, f minus n, right? So your minus n is inside n. Okay, so this is a martingale. So this is something we prove, I think, when we discuss the martingale, right? So for expectation of any random variable condition on the filtration fn, right? That is a martingale. So I said that now here my f minus n, this one is my filtration. So this is a martingale. And okay, and you can see that this is by definition a right close martingale, right? Because your x1, right, is a fit, is basically plays the role of your x inside the definition over here, right? Okay, right, it's a fixed integrable random variable. So for martingale, it means this is equal to this. Okay. So my x1 is plays the role of the x inside my definition. So this is a right close martingale. Okay, so why we need this? So I won't be able to explain the reason why until next week. But just keep in mind that this is a right close martingale, and then next week you will be able to get the basically the strong law of large numbers almost immediately, right, by just setting up your random variables in this way. So again, it shows the power of martingale theory, right? By setting up the martingale in the right way, you get results that are not that easy to prove directly, right? So, right, okay, so today we just proved that it's a right close martingale, and then next week we will talk about conversions of submartingales or martingales, and then we can make use of that result to indeed get to prove that, right, this guy is conversion, and we will be able to show that in fact the z minus n, right, which is Sn over n, is converging to the expectation of x1. Okay, any questions here? All right, okay, so no question. We will stop here today. And then, yeah, have a good weekend and see you guys next week.